So in this particular video, we are going to be introducing the idea of gates that act on a single qubit. Now, the single qubit kind of gates are a little bit interesting in the sense that they can be primarily divided, for the four that we're going to be discussing today, primarily divided into two groups. One where the resultant qubit, this resultant perhaps mathematical model of this qubit, the linear combination, right, is either an identity mathematically. It is pretty much identical to what we started with, or two, it is a not gate of some sort, that should be capital N, of some sort, that arguably can negate the qubit that we have on hand. Now, when we take a look at this, we will note that their general name is known as Pauli transformations, named after Wolfgang Pauli, born in 1900 in Austria, Vienna, Austria. And he died about 13 years or so after the conclusion of World War II. Now, when we talk about Pauli transformations, these are only four of quite a few, actually, single or one qubit gates that we can have. Now, recall what a quantum gate does to a qubit. Either maybe alters, for instance, the orthogonal matrix that we're measuring this qubit in, or two, alters the particular linear combination that we are looking at, the probability amplitudes that we are considering. Now, the four gates that we're going to be looking at today, the four Pauli transformations that we'll be looking at, are gates I, Z, X, and Y. Yes, I, Z, X, and Y in that particular order. Now, gates I and Z are relatively straightforward. They are both known as identity matrices. Now, identity gates. Now, I is relatively probably the simplest one you could ever think of. I is expressed as an identity matrix, straightforward. There is nothing strange about it. And in this case, we're looking at 2x2 identity matrix. Again, recall identity matrices have, a 1 on the major axis and a 0 pretty much everywhere else. Now, let's say we are measuring a qubit that can be expressed as a linear combination A0 plus A1, and I'm just naming the probability amplitudes, right? And so we're saying, hey, I'm going to apply our gate here to our particular linear combination. Now, in this case, what I'm doing here is I'm writing a bit as a function. So we're saying, hey, our input here is our linear combination, and the function we're plugging into is our gate I, right? And so if we rewrite exactly what's occurring here, this is actually a bit of a multiplication problem. So we have our identity matrix being multiplied by this linear combination that we have right over here up in the corner. Now, we can rewrite this linear combination to be something a little bit neater. Recall that 0, just as a kind of scratch paper side note, right, can be expressed as 1, 0, the vector 1, 0, and that 1, our vector here, right, can be expressed as 0, 1. And as a result, if we plug them in, we say, hey, let's say A0 multiplied by 1, 0, plus A1 multiplied by 0, 1, just applying scalar, I suppose you can say scalar multiplication to our vectors, and then adding them directly across, we end up with a lovely vector of A0, A1. And I'll skip these steps going forward. It is relatively nice to know beforehand where we got these vectors regardless. Now, when we take a look at what we have here, we say, hey, all right, so we have this identity matrix being multiplied by A0, A1, and so what happens to it? And so the resultant, actually, if you are familiar with the properties of identity matrices and where in the world they get their name, right, the resultant is a vector that is pretty much itself. We have A0 and A1. If you want to multiply out this particular matrix multiplication problem, you will see that is the case. Simply put, this I gate is pretty much acts as the identity. It leaves these qubits completely unchanged, because we can then rewrite this as saying, hey, this is a linear combination A0, 0 plus A1, 1, and we are done. Now, that is our gate I, right? And so let us consider what is happening with our gate Z. So, like its friend gate Z, right, is also technically speaking an identity matrix, but its effect is slightly different. So the matrix that defines our gate Z is actually 1, 0, kind of similar so far to I, and then 0, -1. And what does this -1 do? So if we are to write and go through the exact same steps as we had before, we have Z with our lovely friend, our initial qubit, A0, 0 plus A1, 1, right? We can rewrite this as saying 1, 0, 0, -1 multiplied by A0, A1, a single vector, right? Which gives us the result, actually, of some vector in the following form. We have A0, and then curiously, we actually have negative A0 at the bottom. negative a1 at the bottom. So you might say, all right, what does this do to change the linear combination that we started with? So if we were to write it out, we have a0 multiplied by vector 0 plus a1 in direction 1. Oops, I'm sorry, it should be minus. And this major change, this little minus here, right, where we're actually finding the difference between a0 and a1, actually has a bit of a curious effect in the sense that it gives us, technically speaking, from a purely mathematical perspective, the same exact linear combination, because if I square a0 still equals a0, if I square a1 still equals a1, if I square negative a1 it still equals positive a1 squared. So there isn't really a change in the probability amplitudes. What we do see is a change in the sign, specifically for our second kind of probability amplitude here, in this case for our vector 1. So what does it actually do? Let's look at what this gate, this Z gate, does a little bit more carefully with a bit of an example here. So let's say that we are measuring in the following way. So just to establish what we already know, we know that Z, putting the vector 0 into our lovely Z gate, is just going to give us the same vector over again. If we put our vector 1 in, it's going to give us negative 1, right? Now, recall the idea of equivalent state vectors. And so equivalent state vectors lets us ask, hey, in what cases are these linear combinations in these vectors, technically speaking, we're representing the spin of a particular qubit exactly the same as we established before? Maybe if we multiply the entire vector, say if we have let me use a different letter here as an example. So we have, say, b0, 0 plus b1, 1, right? And if we negate the entire thing, so if we change all of this to a negative b0 and a negative b1, what ends up occurring? Let me actually negative b1, what ends up occurring is we can say, hey, this is precisely the same exact qubit that we are describing. We have just negated both values. In this case, actually negated in this case is just multiplying by negative 1. I apologize for this abusive terminology. Now, however, we come across this question of what happens if instead of saying, hey, I don't like the signs of both, we only change the sign of 1, and this is what we have done in this case. Let's say the first one remains positive and the second one becomes negative. So what happens here? Now, what was established in this equivalent state kind of description is this idea that actually if we were to, for instance, transfer this particular linear combination to a slightly different perhaps representation of it, and it's different orthogonal bases, right? What ends up occurring is that it could actually be referring to spin in opposite directions. So if we were to say, hey, the plus is going to be referring to spin in the I suppose you could say to the left, right? Then the negative here, if we were to undo exactly what occurred here, the negative value would correspond to measuring spin actually in the rightwards direction. So actually it is worth noting that these are not equivalent states when we attempt to change the orthogonal bases, orthogonal bases that we're measuring them in. So from a technical perspective, Z is not purely an identity gate. It acts very similar to it in the sense that the probability amplitudes are not altered, but it does not preserve all properties of our initial linear combination. Now we move on to our next two gates, gates X and Y, and these are essentially what correspond arguably to our NOT gates. So X here can be written in the form X is equal to our matrix, right, of 0, 1, 1, 0, which is pretty much when we take our identity matrix and flip it. So what is occurring here, right? If we essentially plug it in, we say, hey, let's take our X gate, and I'm just skipping a couple steps here, and multiply it by a 0, and we're going back to our initial qubit here with our initial linear combination. We say, hey, let's multiply it out and see what occurs. And so what ends up happening is we say, hey, all right, so we have on the top, we have a 1, right? And then on the bottom, we fundamentally have a 0, which then allows us to say, hey, this can be written as a 1 multiplied by our vector 0 plus a0 multiplied by our vector 1. And so what we've done here is the fact that we pretty much switched the places, right? And so the gate x just flips our probability amplitudes here. Now, on the other hand, we can consider what occurs with our gate y, right? So again, recall we are trying to make some change to this linear combination. So we have y is going to be equal to 0, 1, and like the z gate, as with the z gate and the I gate, right, it's going to have a -1 instead of a +1. And so when we consider exactly what is occurring when we actually take a linear combination, a qubit of some sort, and apply the y gate, right, we see a0, a1, there's our original combination. Then we say, all right, so we take 0, multiply that by a0, and add that to 1 multiplied by a1. So we have a1 on the top, and actually negative a0 plus 0, so it's negative a0 on the bottom, just verbalizing matrix multiplication again. Now, what we see here again is that we have switched the places. We have a1, 0, but in this case, we have also taken the second term here, in this case, a0, and added and put on actually a negative value on there. And so that is the effect of our y gate and how it changes actually the linear combination we are representing our single qubit with. So just to briefly summarize, we looked at 4 major Pauli transformation, 4 major 1 qubit gates today. This is not all of them. There's, technically speaking, pretty much an infinite amount. But the 4 major ones we looked at are I, Z, X, and Y. Now, I here gives us a direct identity matrix. Z, on the other hand, gives us, oops, that's not the right matrix. Gives us an identity matrix. Z gives us arguably an identity matrix, but it does change the last value, right? And so as a result, the direction we are technically looking in, and when we move it and quote unquote switch it over to a slightly different direction of measurement will actually be changed, right? And x is essentially the same thing, but it is a not operator, and y is our -1 value, the equivalent of z is to I as y is to x in this case. And so these are our 4 Pauli transformation gates. And as always, thank you for listening. If you have any questions, please do not hesitate to visit the Q-munity Tech website. And as always, stay curious and keep on learning.